Hello, everyone. Welcome back. We are ready now for Module 7 of Multivariate Statistics class. And this is the module when we start to learn about strategies for working with missing data. So this is a really handy module, I hope you'll find. This is stuff that we don't always cover in other courses. A lot of times we just sort of take for granted, that, missing data aren't a problem, or that what missing data that we might have in a data set are small enough that we don't have to worry about it. But actually, missing data can really cause quite a few issues. And so you want to learn some strategies to help deal with that. So I have our Module 7 handout here, and I'm going to start a timer to just to make sure this video doesn't go too long. And if so, I can split it up into a couple different chunks. So I've pointed my R Studio interface here to week 7, and now we're ready to go. So first thing we're going to do is we're going to load in some packages. Tidyverse and Psych we know already. NannyR, which I think is some combination of caviar and NA. So it's like caviar for missing values. Which is a goofy name. I know it doesn't make a lot of sense. That is a package that has a lot of tools for visualizing and working with missing data. So we're going to load in the NannyR package. And again, if you don't have that package, you can always go over here to packages and click install. And you can just start typing NannyR and you see it pops up right away. So very easy to add if you need to. Okay, so we got those packages. And then we're going to load in the data, again, using the Haven package, which is our kind of Rosetta Stone for reading in data of different types from other different statistical packages. So these data are called Oregon from Oregon 2004, and I will call it the same thing. I will just call this Oregon when I load it into my environment. There we go. So we've got about 4,508 observations of about 8 variables. All right, so let's glimpse this and get a better sense of what we're looking at. So these data actually come from Alan Aycock in his book, A Gentle Introduction to Stata. So I know I mentioned that book for Stata users. Aycock has a nice chapter on dealing with missing data using Stata tools. And so I adapted a lot of those materials using this data set for R, because R will do a lot of the same things, just with different packages and things. So this is public opinion data from a public opinion survey collected in Oregon in 2004. Alan Aycock was a longtime professor at Oregon State University. And so he's using public opinion data from Oregon. We could collect something very similar from Virginia. So the idea here is that we're trying to understand the relationship between public opinion on a lot of these different issues. So we have an ID variable. COM3 is a measure of concern for the community, sort of a civic mindedness or community mindedness. EPHT3 is, I believe it's concern for education and public health issues. ENV-CON, that's concern for the environment and environmental issues. We have male here, which is a measure of whether the respondent identifies as male. I believe this is only 2 categories. Again, this is pretty old data. Health prob, HLTH-PROB, that is whether or not the respondent reported having any health problems. I think that's binary, just yes or no. I think that's just a yes or no question. Income is annual income measured in dollars, and education is the highest grade level attained in education. And you'll see some of these are, like 16 would be, if we assume 12 is senior in high school, right? 16 would be 4 years of college. Anything above that would be beyond sort of undergraduate training. So we have some measures of income and education. We have some measures of public opinion related to education and other topics. And if you want more details, of course, you can always use this str function. So str, which is for structure, You can do STR and let's just say Oregon $. Let's look at that COM3 since that's our outcome. Okay, so it's actually how much you feel a part of your community. So which number comes closest to how much you feel a part of your community? And I believe it goes from 1 to 5 or something like that. Again, we can check that with the table function. This is a little extra. This isn't stuff that's included in the code, but this is stuff we've covered in past weeks. Yeah, so it's about 1 to 5, how much you feel a part of your community. And so you can see it's pretty heavily skewed, left skewed. So more responses are to the right, with people feeling more a part of their community. Higher numbers mean closer community. So we're essentially trying to predict closeness of community is our outcome. Okay, so let's look at some descriptive statistics. Describe from the psych package. Again, it's a great, quick and easy tool. And I even use the fast equals true option. You don't have to use that, but that just gives you the very basics. N, mean, standard deviation, min, max, and range, and then standard error, which is basically the standard deviation divided by the square root of the sample size, I believe is what that is. So that gives you a sense of the sort of margin of error for each statistic. Okay, so that gives us a sense. And what I want you to pay attention to here, I mean, all this stuff is kind of interesting. You know, most of these are sort of survey measures that we're using, involvement in the community, concern for educational issues, and concern for the environment. They all basically go from 1 to 4 or 1 to 5. So they're all sort of Likert scale items. So that's good to know. And then health problems is binary. And then we have income and education. But what I want you to pay attention to the most is this column right here, which is N. And this is a very useful thing to do anytime you have a data set like this that you may not be familiar with. If you notice, okay, I'm looking in the upper right, there are 4,508 total observations in this data set, rows, right? And so if I have no missing data, then this N should be 4,508 for every single variable. And notice I do have 4,508 ID variables. So that is my only variable that is actually fully observed. All of these other variables have missingness. And the lower this N, the more missingness is present. And so you can see the big difference is, okay, so there's some missingness here for some of these variables, but the big difference here is for income and education. So for income, I'm missing about 700, and for education, I'm missing almost 1,200. So that is an example, and you find this comes up a lot, actually. That would be an example of a data set that has a pretty decent amount of missingness. So 1,200 out of 4,500 is almost, I think it's a little bit more than 25%. So this would be a case where if you wanted to publish a paper or do a dissertation or report, you would probably want to think about some strategies for how to handle that missing data, because there's quite a bit that's missing, and that can cause some issues. So the first thing we do when we're investigating missing data is to run a model, what I call like a naive model, meaning a model where we assume that there aren't issues with missing data and we just run the model that we want to run. So that's kind of the first step. And so we're going to run a regular regression here, and this is going to use what are called complete cases. Now, I talk about this a little bit in the lecture, but most conventional statistical methods that use regression, t-tests, ANOVA, correlation, things like that. And even a lot of the fancier methods we're going to learn about, like cluster analysis, for example, they are what are called complete case methods. So if you have an observation in your data set that is missing a response, then that observation is going to be removed when the model is run. And that's because the most conventional methods don't have good ways of handling missing data. And so the solution is just to kick people out. So that is what something we want to be aware of anytime we want to run models like this. All right, so complete case approaches are very, very common. So let's see exactly what happens here when we run a regular regression model. So let's say we want to predict concern for the environment and environmental issues. And our predictors are how involved you are in your community, health and environmental issue, or education and public health, a measure of male versus female, and then health problems, income, and education. So we know, right, income and education have high levels of missingness. So when we run this thing, we might start to see some big issues. So we look at our results, and you will get results, right? As long as you have observations, you're going to have results. And so just looking at this really quickly, again, we're predicting concern for environmental issues. The more involved in your community, the lower your concern for the environment, which is kind of interesting. The closer you feel to your community, I guess. The more concern for education and public health, the more concern for environmental issues. Individuals who identify as male have also are associated with lower concern for the environment. The more concerned you are with your own health, if you have health problems, you're going to be more concerned about the environment. And then we don't see an effect here for income or education. What we want to pay attention to, so let's say we really want to do something with this model. How many people are in this sample? And we can take a look down here at the degrees of freedom. So see where it says F statistic? Okay, so this is the F statistic for the entire model. So this is the thing that's telling us whether or not our model has any predictive power at all. And it does, right? It has a lot of predictive power. We're actually explaining about 31% of the variation in environmental concern using just these predictors. But the only thing you need to pay attention to are the degrees of freedom. So an F statistic has 2 degrees of freedom. It's DF1 and DF2. And DF1 is 6, and that is equal to the number of parameters that you're estimating minus 1. And these are all the parameters that we're estimating: 1, 2, 3, 4, 5, 6, and we're estimating an intercept, which is 7. So 7 minus 1 is 6. So that's the first degree of freedom estimate. The second degree of freedom estimate is your sample size minus 1. Okay, so there are 2,819 degrees of freedom here, which means the effective sample that was used was 2,820, right? So out of 4,508 people, we're only getting about 2,820, which is not great. And you even get a note here, 1,682 observations deleted due to missingness. So there is quite a bit of data that has been removed here because people just don't have either a response for the education variable or the income variable or both. All right, so that is sort of our problem. That's the problem statement. And now we got to figure out what exactly to do about it. So this is where the MCAR package is really helpful. There's a function in that package, and I've already loaded it up. And the function is called misvar summary. So you can run this on a data frame, and it gives you a nice summary of all the missingness that is present in that data frame. So it gives you all your variables, and then it gives you the number of missing observations as well as the percentage of missing observations. So as we suspected, right, the big issues are with education, 25% missing, and income, 14% missing. I think I mentioned this in the lecture, but people always ask me how much missing data is really a problem. And that's not an easy question to answer, actually, because if your data are MCAR, right, missing completely at random, you can actually have large amounts of missing data and it will not affect your results. It might affect your power, but it will not affect the estimates that you're trying to obtain. And so that's a tough question to answer. But in most places, if you report 25% missing, people will kind of wonder, that seems like a lot. and especially with another second variable that has such a high level of missingness as well. So this is a great table. You can actually pull a table like this into a paper. You could also summarize this in words, just describing, most variables here have less than 1% missingness, or in the case of health problems, 2% missingness, but you really have just two variables that are a big issue. We can also summarize this visually. And this is another package. Yeah, I'm going to throw a lot of packages at you this week. I apologize. They're just missing data is not something that's really built into R. And so we have to rely more on packages. There's a really good package called VisDat, and that allows you to do a cool plot using this vismiss function that gives a nice summary, basically the same kind of summary that we found in the table. So this just breaks down. So here we have the number of observations, and here are our variables going down in the columns. So here's ID, right? And each little slash, each little gray line represents a missing observation. So notice ID is perfectly clean, right? No missingness. A little bit of missingness for these variables, very little missingness for the environmental concern, which is our outcome. But we can see, pretty quickly the big issue is with income and education. And we even get the percentage of missingness here in parentheses, which is cool. So this is basically the same amount of information except for the ends that you get from the table, but you just get it graphically, which is pretty cool. And that also gives you a sense of, if somebody's missing both, like, let's see, we can find somebody here is somebody, this line right here going across, this is somebody who's missing health problems, income, and education. So you can get a sense a little bit of the patterns. Another way to do this is with geom mispoint. This is from the NannyR package. So this just adds on to ggplot. So instead of geom point, which we've done before, you can do geom mispoint. And you do this with a scatter plot. So with one variable on the y-axis and one variable on the x-axis, and they both need to be continuous. So here we have level of education on the x, and we have income on the y. And you get a cool little plot here. So all the teal dots, those represent people who are not missing on either variable. So it gives you a little bit of the sense of the distribution of these scores. And then the coral dots here, so this little diagonal, those are people that are missing on everything. So you don't have, what do you call it? You don't have education scores, and you don't have income scores. And then these teal dots going along the sides, these are people who have one but not the other. So it gives you a sense of sort of what variables are missing and how they might impact your distribution. For example, these observations here, these are all people who have a 10th grade education, right? But we don't know their income. So their income is not represented. These are all people who have 20 years of education, but we don't know their income. This is someone who has, 7 or 8 years of education. And so it gives you a sense, same thing with income, of what's out there, right? So what is out there, and how might these things actually be related? Okay, so just a few tools to explore missingness. This MISVAR summary, which is really good. Of course, the first thing you want to do is figure out just how much data is going to be gone. And we figured that out. We figured if we want to do a regression here, we're missing a ton of data. And then this vismiss function is a really nice graphical summary. And then if you're interested specifically in two variables, you can do the ggplot and make a little scatter plot. So the next thing we want to investigate is what exactly the process is, or the mechanisms of missingness are. And this, if you have not seen the lecture video yet, I highly recommend it. So this gets into, could the data be considered MCAR, missing completely at random, MAR, missing at random, or MNAR, which is missing not at random. This is a really important assumption. It's one that few people talk about, although it's becoming much more popular to address it in papers, because that is really the underlying issue. The underlying issue is not the amount of missing data, it's the process by which the data were missing. If there is some confounding variable or some other piece that is contributing to missingness that you're not accounting for in your model, that can be a big issue, even if you have small amounts of missing data. So to do this, we're gonna do something a little tricky. I have a function to run Little's MCAR test, which is something I talked about in the lecture. But unfortunately, the package that produced this is no longer available. And so all I have is the code, and we have to sort of input this and create our own function. It's almost like our own little package that we run inside R. And so to do this, you open up the R code that came with this week's materials, and it's called mcar-test.r. So this is our script. So I just click it, it opens right away. And notice I get a little message here, package norm is required but not installed. So I want to install that. And you may get the same message when you open yours. So here we have our function, right? And what this will do, we don't actually have to touch any of this code. All of this will just run on its own. And it will actually run Little's MCAR test. So what this is going to do is it's going to create a function called MCAR test using this function, function. It's actually a function, right? It's going to create a function that we then can use inside of R. So you don't have to play with this code at all. It should just run. So I'm going to click here. I'm just going to click run. And oh, that was just, oh, good lesson. That just ran the line. So I'm going to click here and I'm going to go to, I'm going to highlight this whole thing like that all the way down to the bottom and then click run. There we go. So that's better. So that little nvar we can ignore. What we really need though is the function. So this thing is now loaded up. I just highlighted everything and I clicked run. I think you can also click source as well, and it'll run the whole thing. And now MCAR test is actually something I can access in my environment. So I'm going to run the MCAR test on the Oregon data set. And the way this works is you get a chi-square statistic, you get a degree of freedom, and then you get a p-value. And you basically cross your fingers and hope that this p-value is non-significant, because that shows that the data may actually be MCAR, even though that's something we can't actually prove. In this case, we're not even close to a non-significant p-value, which makes sense because we have a lot of missingness. Income and education are often variables where people choose not to respond for a lot of reasons. So this is 0.0000008. So this is a very small p-value. You also get a nice measure of distinct patterns of missingness, which is kind of interesting, but you can't really do much with it in this case. So long story short, our data do not meet the MCAR assumption, which is a big bummer. But that's cool because it gives us a little bit more to do. All right, so I'm looking at my timer and I think this might actually be a two-part video. So just to recap, in part one, we talked about all the ways that you can explore missing data. So we talked about graphical exploration, we talked about a summary using a summary table, and we talked about just sort of running a model and seeing how much missingness we have to deal with. In part two, we're going to do some logistic regressions to try to understand which variables might explain missingness. And then we're actually going to do multiple imputation using the mice package, which is one of the most recommended approaches for handling missing data. So that's all ahead in part two. Hope you found this helpful, and take care.